Hello and good day, everyone. We are from Group 8 for the course code KM44203 for heat transfer, and this is our group project presentation. So these are our group members in Group 8. We have Darren Dane Jeffrey as project leader, me, Alan Lewikin, as secretary in this group, Rendell Dyer Sayurian for R&D, Muhammad Alif Haikal bin PA for presentation, and Wilson Low Wishong for analysis lead. So let's get into it.
Hi, my name is Wilson. So, biomass drying is an important process because it helps reduce the moisture content in biomass. So, when the moisture is reduced, the biomass become easier to handle, store, and use. However, the drying process must be controlled properly. If the airflow is too low or uneven, the drying process becomes slow and may not be uniform. On the other hand, if the temperature is too high, it may damage temperature sensitivity biomass materials. Because of this, our project proposed an indirect LPG fired air heater. In this system, LPG is used as the heat source, but the combustion gas does not directly touch the biomass. Instead, heat is transferred through a tube and a fin radiator, while a centrifugal fan supplies forced airflow into the drying chamber. And this design helps to provide cleaner and more controlled hot air for the biomass drying process. So now let's go through the objective of this project. The first objective of this project is to design an indirect LPG fired air heating system using a tube and heat exchanger and a drying chamber for biomass drying. The second objective is to calculate the heat duty, required process airflow rate, and estimate LPG consumption needed to supply controlled drying air. The third objective is to use CFD simulation to evaluate the system performance. This includes studying the temperature distribution, airflow pattern, pressure drop, and convergence behavior of the proposed heater dryer system. The final objective is to propose control and safety measures such as airflow regulation, instrumentation, safety feature, and scalability improvements. These measures are important to ensure that the drying air temperature is maintained at or below 70 degrees Celsius. So let's go through the problem statement. The main problem in this project is to design a system that can supply clean and controlled hot air for biomass drying. The system must maintain proper airflow through the heat exchanger and drying chamber. It must also ensure that the hot air temperature does not exceed 70 degrees Celsius so that the biomass is not damaged during drying. Another important issue is safety and air cleanliness. Since LPG combustion produce gas, the system must prevent the flue gas from coming into direct contact with the biomass. This is why an indirect heating system is used. So, however, this project only focuses on the air heating system. It does not fully validate the actual drying capacity because wet biomass and moisture evaporation were not included in the CFD simulation. Therefore, this project mainly evaluates whether the proposed air heater can produce controlled airflow and temperature suitable for biomass drying.
Hello, I'm Randall. So next I will present the literature review for the proposed indirect LPG-fired air heating system for biomass drying. Firstly, the heat and mass transfer principles are important to understand the drying process. In this system, heat transfer occurs through two main mechanisms. Heat is conducted through the copper tubes and aluminum fins of the heat exchanger, and then transferred to the process air through forced convection. The useful heat transfer rate can be estimated using the equation Q equals m dot air times Cp of air times the temperature difference between the outlet and the inlet air. This relationship is suitable for initial system sizing when kinetic and potential energy changes are negligible. However, during the actual biomass drying, heat transfer alone is not sufficient. So the evaporation of moisture from biomass also involves mass transfer that depends on the factors such as moisture content, porosity, diffusivity, and equilibrium moisture conditions. Secondly, previous studies on indirect forced convection dryers show that separating the heat source from the drying product provides cleaner and safer drying air. In this type of system, a fan forces heated air through the drying chamber, and research has shown that dryer geometry and operating conditions strongly affect airflow behavior and temperature uniformity. Safety studies also highlight that predicting drying performance requires considering both heat and mass transfer, especially when moisture removal from the biomass needs to be evaluated. Based on the literature review, several important design considerations were identified. For temperature control, both fuel input and airflow rate must be regulated because low airflow with constant heat input can increase the outlet temperature. For the heat exchanger design, copper tubes and aluminum fins are selected because they provide high thermal conductivity and larger heat transfer area while keeping combustion gases separated from the drying air. For airflow distribution, the fan, transition duct, and chamber geometry must be designed to prevent direct airflow short-circuiting and ensure uniform air circulation. For CFD analysis, important parameters such as temperature distribution, velocity, pressure drop, and convergence behavior should be evaluated. Additional factors such as humidity and biomass moisture kinetics are required for more accurate drying prediction. Finally, for the air movement system, a forward curve fan was selected because the design focuses on compactness and suitability for low-flow duct applications. Although backward curve fans generally provide higher efficiency, the selected fan provides a better balance between size and system requirements. In summary, the literature review provides the fundamental understanding of heat and mass transfer, indirect drying principles, and key design considerations that guide the development and evaluation of the proposed biomass drying system. Thank you.
Hello, I'm Alif, and I will present on the methodology part. So our work focused on developing a prototype scale indirect LPG fired air heater, which means the system was designed so that combustion gases do not directly contact the process air entering the drying chamber. And then, using SolidWorks flow simulation, we want to evaluate its airflow and heat transfer behavior. For the system design, as you can see from the figure, the system is divided into two main flow paths. The first path is the combustion gas path. The LPG is supplied to the burner or combustion chamber, and then the hot combustion products will pass through the copper serpentine radiator with aluminum fins before exiting through the flue gas exhaust. Whereby the second path is the clean process air path. The first process is the ambient air at 30 degrees Celsius is supplied by the forward curve fan into the heat exchanger housing, and then the air absorbs heat from the radiator fins and then enters the drying chamber. This arrangement makes the system an indirect fired design because the clean process air and combustion gas are separated. Other than that, the system also includes a control and safety function. The RTD and airflow sensor provide feedback to the PID controller, and then based on the measured drying air temperature and airflow condition, the controller adjusts the LPG valve and fan speed to maintain the drying chamber temperature below the 70 degrees Celsius limit. And if gas leakage, flame failure, low airflow or excessive temperature is detected, the LPG valve closes and the alarm is activated. As you can see in the figure, the main components used in the model are shown. The system consists of the combustion chamber, radiator inlet pipe, radiator exhaust pipe, heat exchanger housing, copper serpentine radiator, aluminum fins, centrifugal impeller, and drying chamber. Let's go through to the working principle of the LPG indirect air heater. First is that the fan passes air through the heat exchanger housing and around the radiator fins. Then heat is transferred from the hot flue gas inside the radiator tube through the copper tube wall and aluminum fins, and finally to the processed air by forced convection. The table in the slide shows the selected design for each component. And for the heat exchanger, it was designed as a copper serpentine tube with 30 aluminum fins. Copper was selected for the radiator tube because of its high thermal conductivity, while aluminum fins were used to increase the external heat transfer area. For the fan, a forward curved centrifugal fan was selected because it is compact and suitable for low-flow ducted airflow. Meanwhile, the drying chamber uses a rounded rectangular geometry to provide internal volume for air mixing. For control and safety, the system includes an RTD or thermocouple, airflow sensor, PID controller, LPG control valve, flame sensor, gas detector, high temperature trip, and purge system. Moving on with the principal geometry for each part of the system, the main radiator geometry consists of a 10 mm outer diameter tube, 9 mm inner diameter tube, and a 0.5 mm wall thickness. The radiator uses 30 fins with 8 mm spacing, giving a total fin surface area of about 0.6 meters squared. Other parameters such as heat exchanger housing air volume, drying chamber air volume, and process air inlet and outlet area are shown in the table. The main assumptions were steady state internal flow, ambient air temperature of 30 degrees Celsius, atmospheric outlet pressure of about 101,325 Pascal, and air properties of 1005 joule per kilogram Kelvin and density of 1.165 kilogram per meter cube. Meanwhile, the housing walls were treated as adiabatic, so external heat loss and radiation were not included in this prototype simulation. The CFD simulations and analysis will be presented by Darren.
Greetings. In this flow simulation section, we will discuss the velocity, the temperature, and also the pressure distributions. However, we have four main components here. We have the combustion chamber, the impeller housing, the radiator housing, and also the drying chamber. However, in this simulation, we only focus on the impeller housing, the radiator housing, and in the drying chamber, whereas the combustion chamber and the sensors and the valves will be explained conceptually. This slide, it shows the full modeling layout for our LPG fired air heater and drying chamber system. So the main concept is an indirect heating system where the LPG combustion gas does not directly enter the drying chamber. Instead, the combustion heat is transferred through the radiator pipe and fins and to the air, while the impeller supplies air through the radiator housing into the drying chamber. The purpose of the simulation is to check whether our system, can supply heated air close to 70 degrees and does not exceed 70, while maintaining also proper airflow. In this slide, it focuses more on the radiator model, and which is our main heat exchanger in our drying system, LPG drying system. The radiator has a 10 mm outer diameter and an internal diameter of 9 mm, so it has a thickness of 0.5 millimeters, and this pipe along the radiator carries the hot flue gas from the combustion chamber, while the external radiator fins transfers heat to the surrounding airflow before the air enters the drying chamber. So there are a total of 30 cooling plates with a 8 mm spacing, so this in a way improves heat transfer through conduction from the pipe to the fins, followed by forced convection from the fins to the air. For the simulation, the combustion chamber was assumed to produce a hot flue gas at approximately 500 kelvins, and as it travels through the radiator pipe, the temperature gradually decreases to around 414.15 kelvins, as we can see in the SolidWorks simulation above. Through our calculation, we assume that the mass flow rate is 0.0045 kilograms per second, with specific heat capacity for flue gas is 1110 joules per kilogram Kelvin. And the temperature difference we calculated from our SolidWorks simulation, which started with 500 kelvins and drops all the way to 414.15 kelvins. So we have a total difference of 85.85 kelvins. So From this radiator pipe simulation, the heat transfer rate was estimated to be approximately 43 watts. So this value was then brought forward into the next simulation as the radiator fin heat source. Based on previous calculations for the heat exchanger and the required mass flow rate, we tried to see what rotations to get our target velocities and our target mass flow rates. So in here we can see our forward curve centrifugal fan simulation to supply air into the radiator housing. So the impeller was set to 120 rpm because this speed produces airflow the closest to the required target, which is 0.001 kilograms per second. From the flow trajectories, we can see that the air enters through the circular inlet pipe and rotates through the impeller region and is then guided by the volute housing towards the rectangular outlet. The pressure difference is very small, which is expected because the airflow requirement is low and the fan is only used to provide gentle forced convection. Therefore, 120 rotations per minute was selected as a foot-suitable fan speed. Based on previous calculations for the heat exchanger and the required mass flow rate, we tried to see what rotations to get our target velocities and our target mass flow rates. So in here we can see our forward curve centrifugal fan simulation to supply air into the radiator housing. So the impeller was set to 120 rpm because this speed produces airflow the closest to the required target, which is 0.001 kilograms per second. From the flow trajectories, we can see that the air enters through the circular inlet pipe and rotates through the impeller region and is then guided by the volute housing towards the rectangular outlet. The pressure difference is very small, which is expected because the airflow requirement is low and the fan is only used to provide gentle forced convection. Therefore, 120 rotations per minute was selected as a foot-suitable fan speed. From our previous impeller simulation, we also set surface goals on the outlet impeller housing towards the radiator inlet. So this is where we appoint surface goals to see the mass flow rate, also the volume flow rate. So from that we can see that the mass flow rate has a value of 0.0010624 kilograms per second, and also for the volume flow rate is 0.000882637 meter cube per second. So these values are close to our theoretical values, meaning that our 120 rotations per minute for impeller centrifugal fan is accurate and suitable. The outlet pipe of the impeller housing, we also did contouring to see the average velocity at the outlet, and we calculated that the average velocity is 0.184 meters per second. Based on theoretical calculations, our average velocity is 0.179 meters per second. So the values are close and consistent. To further validate why we choose 120 rotations per minute, we did our fan simulation and mass flow validation again across with using our radiator housing. So from the fan simulation, we get the average inlet velocity at the radiator housing of approximately 0.19012 meters per second, which we can see in the table of the surface goals that we have. The air density was assumed to be 1.165 kilograms per meter cube at approximately 30 degrees Celsius at 1 atmospheric pressure. Using the same inlet opening of 80 by 60 millimeters, the simulated volume flow rate is 0.0009 meter cube per second, and the corresponding mass flow rate is 0.00106 kilograms per second. So this is very close to our initial theoretical required mass flow rate of 0.00107 kilograms per second. So therefore, 120 rotations per minute was selected because it provides the required airflow for the radiator housing. Slide, we can see the temperature cut plot at the radiator housing and the drying chamber. After the air passes through the radiator housing and enters the drying chamber, these three temperatures readings were taken, which is 342.76, 342.74 and 342.69 kelvins. So with these values, we get the average chamber temperature of approximately 342.73 kelvins or 69.58 Celsius. So this result shows that the chamber temperature is very close to 70 degrees and does not exceed the limit. So this small difference between the three readings also show that the heated air region is distributed evenly inside the chamber, with no major hotspots or cold regions. Therefore, the selected airflow rate of 43 watts radiator heat source is suitable for maintaining the required drying temperature. In this is the airflow cut plot, and we can see the airflow direction inside the heat exchanger housing and the drying chamber. The air enters from the right side, which is where the inlet and the impeller outlet is, and inside the radiator housing, airflow forms recirculation zones, which are useful because they increase the air residence time around the heated fins. After entering the drying chamber, the airflow spreads and circulates across the chamber instead of moving directly in one straight path, which we can see in the airflow trajectories. This recirculation is needed because it helps distribute the heated air evenly throughout the chamber and supporting a stable and uniform drying temperature. Therefore, the vector cut plot supports the design because the airflow pattern helps sustain even heating inside the drying chamber, which you can also see in the temperature cut plot. This is the flow trajectories from the heat exchanger housing into the drying chamber. The heated air first passes through the radiator fin similar, and then it will enter the drying chamber through the connecting duct. Once inside the chamber, the airflow forms a large circulating pattern instead of moving directly to the outlet, which is very useful as heat is distributed more evenly throughout the chamber, supporting the average temperature of around 69.6 degrees Celsius uniformly across the drying chamber. So this drying chamber is actually utilized as a structure. We implemented a curved rectangular structure for these recirculation zones. Therefore, the flow trajectory result supports the drying chamber design because the recirculation helps maintain stable and uniform heating for the drying process. In this cut plot, we can see the pressure distribution through the heat exchanger housing and to the drying chamber. The highest pressure region is located inside the radiator housing, where the fan pushes air through the radiator fins as the air moves through the connecting ducts and into the drying chamber. This is because the volume of the air is compressed because of the presence of the radiator. And as the air moves through the connecting duct and into the drying chamber, the pressure gradually decreases. From the scale, we can see in our simulation, the pressure drops at around 0.43 pascals. So this pressure drop is very small because the airflow rate is very low, around 0.00106 kilograms per second. Based on our calculated, we implemented into our simulation, our flow simulation. And the inlet velocity is only around 0.19 meters per second. Therefore, the system does not create major flow resistance, and the selected fan speed is sufficient enough to move air through the heat exchanger and the drying chamber uniformly, spreading the uniform air temperature. In this slide, we implemented surface goal results at the outlet of the drying chamber. The outlet mass flow rate is approximately 0.0010623 kilograms per second, which is almost similar or close to the values of our theoretical results, which is 0.001 or 0.00107 kilograms per second, meaning the speed of the fan or the impeller centrifugal fan is 120 rotations per minute is suitable. So we can see in the simulation the output bulk average fluid temperature is 342.859 kelvins, which is approximately 69.709 Celsius. This confirms that the drying chamber outlet temperature is approximately 69.7 degrees Celsius, which is close but does not exceed the target limit of 70 degrees Celsius. The inlet velocity is also stable at 0.190121 meters per second, showing that the airflow entering the heat exchanger is consistent. Overall, the achieved surface goal confirms that the system can maintain the required airflow and the drying temperature using 43 watts radiator heat source and 120 rotations per minute impeller speed.
Alright, so for this part of the section, I will be explaining how the LPG fired air heater is being controlled and what happens in an uncontrolled operation, and how the design can be improved for the environmental performance. In this section, I will also talk about the scalability as well as the limitations of the project. Okay, so from previous discussion, Darren already talked about the simulation result represents a controlled operating point. So we know that the key operating values are 70 degree Celsius temperature limit, 43 watts heat input, and approximately 0.001062 kilograms per second of airflow, and RPM speed of 120. So what happened in an uncontrolled operation? So uncontrolled operation, the LPG flow and airflow are fixed. So the system cannot correct changes such as reduced airflow or extra heat loss. So if the airflow drops while heat input remains constant, the drying air temperature may exceed 70 degrees Celsius. So in a controlled operation, the temperature and airflow have feedback, so which are sent to the PID controller, and the controller reduce either LPG flow or increase fan speed to maintain the process air temperature below the safety limits. Alright, so now for the environmental and sustainability consideration, we know that LPG is still a fossil fuel, so that still remains as a limitation because it emits carbon emissions. So compared with other renewable heating energy. However, the indirect fire configuration improves the product safety because the combustion gases are kept separated from the clean process air. And then the 70 degrees Celsius control strategy also reduces unnecessary overheating, fuel waste, as well as product degradation. So for future sustainability, we can include improve chamber insulation, minimize air leakage, recover exhaust heat, preheat using solar energy, as well as reduce LPG consumption. So now let's get into the scalability discussion. So we know that this current design is a small scale prototype. It only operates at a low heat input of 43 watts at about 0.001062 kilograms per second of airflow and only a low of 120 RPM fan speed. So this is only suitable for studying heat transfer behavior, and also airflow distribution, but it cannot be directly scaled up to large drying capacity, such as 1000 kilograms per hour. So to scale up, we have to take the first step to calculate the water removal rate and the heat needed to evaporate the moisture from the biomass. After that, we also need to redesign and verify the burner, the heat exchanger, fan, ducting, and as well as drying chamber. So now onto our prototype limitations and improvements. So the prototype has several limitations. The CFD model only focuses on airflow and heat transfer behavior, so it does not actually predict the real biomass moisture removal. The moisture evaporation should be added to estimate the drying rate, final moisture content, and drying time. Mesh independence also should be included so that it improves the reliability of the simulation. The fan performance should be validated using a measured fan curve. Finally, experimental testing using temperature sensors, airflow sensor, and as well as pressure measurement will be needed before the design can be used confidently. Alright, to conclude our presentation, this project successfully analyzed the indirect LPG fired air heater using SolidWorks CFD and heat transfer calculation. From the simulation, we know that the required process airflow rate is 0.00107 kilograms per second for 43 watts heat input. And at fan simulation, for 120 RPM, it produces 0.19 millimeter per second inlet velocity and 0.001062 kilograms per second of airflow, which is very close to the required process airflow. The CFD result also shows that the bulk outlet temperature is 69.71 degrees Celsius, which is below the 70 degree Celsius limit. The pressure drop was also low at about only 0.43 pascals, showing low flow resistance. We also included PID control, safety shutdowns, and further validations are recommended. Alright, that is all from our group. Thank you very much for your kind attention.